Yeah. Give me 1 second. It doesn't allow me to share the screen.
Stacy?
Just a moment.
Thank you.
It says anyone can share, so I don't know what the issue is.
Okay, fine. So then we're gonna go. It could be the case that there is a problem on Moi's side. Hopefully, Ali, did you try? It's gonna be okay on your side.
We tried before,
Okay.
so hopefully it works.
Okay, fine. Okay, great. Good afternoon, everybody. Thanks for joining today's NCCAV seminar. As you are aware, these seminars are that we do have on NCCAVs are once a month, last Friday of the month. The previous seminars are all available on the NCCAV website. And as Dr. Hajbabaie mentioned, our next seminar on by NCCAV is going to be on August 27th. We would like to thank the sponsors of the project, North Carolina Department of Transportation, for enabling this research and creating this forum. We also thank the gold sponsors of the project, Downtown Greensboro, Verizon, and Real Time Innovations, RTI. With that, I would like to introduce today's speaker. We are delighted to have Dr. Ali Hajbabaie as the speaker for today's seminar. He received his Bachelor of Science and Master of Science degree in Civil Engineering in 2003 and 2006 from Sharif University of Technology in Iran. He then obtained his second Master of Science in Industrial Engineering in 2011 and a PhD in Civil Engineering from University of Illinois at Urbana-Champaign. He has been assistant professor in the Civil Construction and Environmental Engineering Department at NC State University since fall 2019. Prior to that, he was assistant professor in the Department of Civil and Environmental Engineering at Washington State University from 2014 to August 2019. He has been the member of different TRB committees. In particular, he has been the chair of the Asset Management Subcommittee of Traffic Signal Systems Committee at TRB, and has been serving as the associate editor of the IEEE Transaction on Intelligent Transportation Systems. Please join me to invite Dr. Hajbabaie for today's talk. Thank you.
Thanks a lot, Ali, for the presentation, for the introduction. I'm just trying to share my screen. So it should be shared. If it's okay, let me know and I go ahead.
Yes.
You're fine.
Okay, very good. Thanks a lot for the introduction, Ali. I want to welcome and thank everyone for taking the time to attend my talk today. I will be talking about traffic control in the era of connected and automated vehicles. And my objective today is to provide you with a high-level overview of the work that we have done over the past few years. I'm not trying to get into all the details, but some details if necessary. Before starting, I'm sure everyone is familiar with these terms, but I'm going to go through them quickly so that we are on the same page. Connected vehicles, as you know, are vehicles that are equipped with communication hardware. They can communicate with each other and with transportation infrastructure. There is no assumption of automation in these vehicles. We have automated vehicles. These are vehicles that some automation is present in them to either assist the human driver or take over the entire driving. In the talk that I have, my focus is mostly on level 4 or 5 automation, and the assumption is that the human driver doesn't do anything. And when we bring the two technologies together, connectivity and automation, we have connected automated vehicles. Not only these are automated and they can drive on their own, they can communicate with each other and with the transportation infrastructure. And what we really use or have used in our work mostly is connected and automated vehicles. So here I'm showing you a typical intersection. You see a traffic light. Of course, we have more of those on each approach. Here, I also am showing you these rectangles. These are loop detectors that we put in pavements. What they do is that they sense the presence of a vehicle, communicate that with a traffic controller that we have there, and that traffic controller comes up with timing for green and other phases so that they can control the traffic. This technology has been around for many years and it works really fine. And one of the issues that we may have with this technology is that these detectors are point detectors. What that means is that while they know if a vehicle is present on them or not, they're not going to have any idea about what is happening upstream of them or downstream of them. So they don't know when a vehicle is going to arrive, what is going to be the speed, and a lot of information like that. As a result of that, if we have those informations that could become available to us by connected vehicles, we can come up with significant improvements in traffic operations. So let's take a look at this figure, this slide, and I'm going to start moving from left to right. And this pretty much is a good representation of what we have done over the past few years in the area of connectivity and automation. And then I'm going to talk about some of these with a little bit more details. So on the left-hand side, you see one intersection. I'm not showing loop detectors here. They could be there. But you see that some of these vehicles are connected. And as a result of that, now we know their location when they are approaching the intersection. We know their speed. We can estimate their arrival time. And as a result of that, we can significantly improve the efficiency of traffic control. And that's what we have been doing in 2017, 18, and published a good number of papers on that topic. Now, when I move one figure to the right, here you see that I have some blue cars. These are CAVs. And then I have some other cars that here I have assumed they are connected. They don't have to be, but now we have a mix of connected and connected, automated, and human-driven vehicles. Now, compared to the previous condition, we can optimize the trajectory of these CAVs so that they go through the intersection a little bit more efficiently. And as a result of that, traffic operations could be improved. Now, what if we don't have any human-driven vehicle in the traffic stream? That takes us to this figure, the second from the right. Now we can go crazy and remove the traffic light altogether. And what can happen here is that CAVs can talk with each other or communicate with a central controller. They can negotiate and find trajectories that are safe for them to go through the intersection without the need to have a signal there to stop the movement altogether. And when we do this, we see significant improvement in traffic operations. But of course, there are a lot of assumptions that are there. For example, you don't see any pedestrian there or other users. We assume that the communication is perfect and so on. And the last figure, or the first one from the right, is pretty much the same concept, a mix of connected automated vehicles and human-driven vehicles in a roundabout. That I will be talking about that too today a little bit, and we see how we can improve traffic operations in other transportation facilities when we have connected automated vehicles. Now, one of the topics that I want to talk about today is what we introduced a couple of years ago as white phase. And the idea here is to use CAVs as mobile traffic controllers. So CAVs pretty much take over the control of the flow of traffic and cooperate with each other and with the traffic light there, so that they form groups of human-driven vehicles and navigate them through the intersection. And what happens during this period of time is that human-driven vehicles just follow the vehicle in front of them. And this cannot happen, let's say, during green or other phases. And I show you on the next slide why. So for that reason, we introduced a new phase, and we called it white phase. It could be any other color, or maybe a flashing green or something that could be used to communicate this regime with other drivers, that at this point you need to follow the vehicle that is in front of you, and CAVs during that time pretty much take control of the flow of traffic in an intersection. Now, this can pretty much work under all CAV market penetration rates. So if you don't have any CAV, this new phase is never going to be activated. We are going to have green, yellow, and red. And what we do is that we either only optimize the signal timing, or we use some information from other vehicles to just improve it. Now, if we increase the penetration rate of CAVs, we are going to get into the situation that we have enough CAVs. So the white phase is going to be activated, and CAVs are going to form those vehicles group and navigate them through the intersection. And when we don't have enough CAV, just red and green. If all vehicles are CAV, what happens is that this is going to pretty much act like a signal-free intersection control, because the white phase is going to be always on, and vehicles all CAVs are going to go through the intersection. Now, the good thing is that if you have a pedestrian and you have a push button, they can just push it and they will receive their own signal. Now, the good thing here is that when we have more CAVs and we have more white phases, the phase transition is going to be reduced. There is not much need to jump between red and green so that we can allocate green to other phases. We just have white phase, and we get rid of that phase transition, which eventually reduces the lost time and increases intersection capacity. So here you see one intersection, we have white phases. Again, you can see that these blue CAVs controlling the flow of vehicles. One may ask why we don't use greens at the same time. The reason is that if we have greens for two conflicting movements and you don't have CAVs right there, human-driven vehicles are going to assume the right of way, and we are going to have crashes. We don't want to have that. And green and red, I mentioned, if we want to just use those, there's going to be a lot of phase transitions and lost time. So we have this concept, and I want to tell you our approach in creating this concept, in testing it, and then interpreting the results that we have. So these few steps that I'm showing here, and I'm not going to show in other topics that I will be talking about today, pretty much is used in all of the, most of the work that we are doing in this area. So we start with a mathematical modeling step. So we develop an optimization model to pretty much represent this concept that we talked about. It could be a linear program, a mixed integer linear program, or a mixed integer nonlinear program. We develop a solution algorithm to solve it and find optimal decision variables there. We almost always start with using commercial solvers, and almost always they don't work because these optimization programs are quite computationally complex. They have nonlinearity, sometimes non-convexity, and it's very hard to solve them with available commercial solvers. So what we do is that we simplify them, we make them small, we use these solvers so that we can get a good idea about how the formulation works, but we almost always end up developing decomposition techniques or use distributed optimization to solve this problem. Then we implement the approach, the solution algorithm. So far, we have done so in a traffic simulator, and we mostly use vSim for this approach. We can do hardware in the loop, especially for communications if needed. And when we do that, we create a lot of scenarios for testing and evaluation so that we can see if the answers that we get make sense or not. Sometimes they don't, and then we go back and see if we need to make any changes in our mathematical modeling or other parts, or maybe that's a valid answer and it's just not intuitive. So I want to go through the problem formulation, and I'm not.
May I have one question?
Yeah.
Okay. May I have one question? If in the previous slide,
Sure.
maybe if I'm patient and see the problem formulation, that helps. But may I know if that formulation is going to be having the horizon that you are simulating. Is it going to be for the entire simulation, or no? You do have it for a limited horizon, and iteratively you're gonna simulate it.
Yeah, it's for a planning horizon, not the entire study period, and it's mostly like an MPC or a receding horizon that we observe network state. Based on that, we optimize and implement for a few time steps, and then we go forward.
Thank you.
No problem. I'm gonna talk about that in not the next, the one after that. So problem formulation, I'm not showing any mathematics here, but mostly concept. Decision variables are the acceleration rate of CAVs. We have state variables that are the location and speed of vehicles that are connected. The objective function that we mostly use is equivalent to travel time minimization. So we want to minimize travel time of all vehicles in that intersection. We have a number of constraints, and here I'm just showing groups of constraints. Each of these have a number of constraint sets. We have vehicle dynamics constraints. For example, for CAVs, we use fundamental equations of motions to update their speed and location based on the acceleration rate. We want speeds and acceleration rates to be within reasonable ranges. We don't want to see too much changes. For example, pushing the acceleration pedal up to the end and the gas pedal and then the brake pedal over and over. So we have constraints or terms in the objective function to prevent those. We have a set of safety constraints. We don't want any pair of vehicles get too close to each other when they are following one another, or when they are passing the intersection and they are on crossing conflicts. We have a number of constraints for signal timing. And for example, in this specific white phase concept, so we had to add a lot of constraints to define the white phase and make sure that the duration is right, make sure that the vehicle follow the signals, and also how to transition from white phase to green or red, and vice versa. And I talked a lot about CAVs forming groups of vehicles. We have a number of constraints that deal with how these vehicle groups are formed, how their length is going to change over time, which vehicle belongs to which vehicle group. So here it goes back to the question that Ali asked. We have a receding horizon, and the reason that we don't solve this optimization program for the entire study period, really two main reasons, if not more. The first one is the computational complexity, because when you want to solve this for the entire study period, the number of decision variables are a lot more, right? So what we do is that rather than, let's say, solving it for 15 minutes or an hour, we solve this for, let's say, 20 to 30 seconds. And what we do is that over this planning horizon, we optimize signals, we optimize trajectories, we do a lot of prediction and optimization there, and then we implement those in vSim for the next couple of time steps. So this could be half a second or 1 second. And then this whole process is repeated until the end of the study period. The second reason is that we want to be able to observe the state of the network and make sure that we can respond to any changes that we have there, and this receding horizon framework allows us to do so. Now, this approach that I'm showing you here, we used it and solved the problem, but the runtime was not very good. So what we did was that we distributed this optimization program to vehicle to CAV level. That means that rather than solving one optimization program over and over for the entire intersection, each CAV solves an optimization program. And what they do there is that they vote for signal timing parameters that are going to be shown on the traffic, on the signal head. And also they optimize their own trajectory, and they coordinate their decisions with each other so that they reach consensus on both signal timing and trajectories. And that significantly improved the computational complexity, and we could get solutions more efficiently. So let's jump over some numbers. And here I'm showing you a case study, 4-leg intersection with exclusive true and left lanes. We are not showing or using right lanes because they don't change the complexity of the problem much, but without them, it's cleaner to see the trends here. I'm showing 4 demand levels that we have tested. We have tested a lot more, but these 4, you see that the demand level starts from 300 vehicles per hour per lane on the true lanes, goes up to 1200. And just as a reference point, a good number for the capacity of a true movement lane group is somewhere in the order of 900 or so in a signalized intersection. And you can see that 2 of the demand patterns that we are using are either at capacity and more than that. So if you have, let's say, 1200 vehicles per hour per lane in a signalized intersection, now you're going to see long queues and really a bad level of service to go through that signalized intersection. So here on this slide, I'm showing you total travel time on the y-axis On the x-axis, you see CAV market penetration rate going from 0% to 100%. And you also see actuated. So this is pretty much the state of practice now for signal control. And at 0%, we don't have any CAV. We are not going to have any white phase. And if you want to really compare actuated, you need to compare that with this 0%. So this shows that our algorithm, even without CAV and activation of white phase, does a little bit of a better job in controlling the traffic that goes through the intersection. But as you increase the penetration rate of CAVs, you can see that we see significant reductions in total travel time. And when we get to 90% or 100%, the travel time is pretty much really low compared to the higher numbers that we have. And we are showing you the trends for all 4 demand patterns that we have here. So this is really a macroscopic view of the things that are happening at the intersection. On this slide, I'm showing you vehicle trajectory. So each line pretty much represents how a vehicle is going to approach the intersection and go through the intersection. On the y-axis, we see distance. On the x-axis, we have time. So if you see a line that is like the one that I'm showing you here, this means that the vehicle approach the intersection and go through without any changes in its speed. But if you look at this line, you see that the vehicle hit the green, the red light, it had to stop, and then it went through the intersection. So if you see bends and horizontal lines, that means that the vehicle is changing the speed. If it's horizontal, it stopped and then goes through the intersection. So 10% CAV penetration rate, mostly you see green and red signals. Actually, I wasn't expecting to see any white, but you can have that. And you see that vehicles come to arrive the intersection, they stop, and when they receive their green light, they go through. Here I'm showing you 50% CAV penetration rate. You see some white phases that are active, and you still see green and red phases. And it's good to see now, if you look at this line, the blue line that I'm showing you here, this is a CAV. Blue lines are CAV, the red ones are human-driven vehicles. So you see that here we have a white phase, but this CAV reduces the speed, stops, because it wants to accommodate another group of vehicle to go through the intersection on a crossing movement, and then it speeds up and goes through the intersection. And by doing that, it controls the trajectory of another CAV and 2 HVs that are in the same vehicle group. And then the next CAV again does that. Now, when we increase the CAV market penetration rate from 50% to 90%, now you don't see many human-driven vehicles. You see mostly white. Sometimes we still need to use a red signal if we have a lot of non-connected automated vehicles on different approaches. And now you see that the traffic goes through the intersection much more smoothly. So the question that we may have here is that this improvement that we observed macroscopically and microscopically, is that a result of having the white phase there, which reduces the phase transitions, or is that because we have a bunch of CAVs, we optimize their trajectory, and we also optimize signal timing? And to answer that question, we defined a new scenario here that I'm calling it no white phase. So what that means is that in this optimization program, we do not allow white phase to be used. So the decision variables for white phase are pretty much inactive or removed from the optimization program. But This optimization program still optimizes the duration of green and red and also the trajectory of CAVs. So here I have 0% CAV penetration rate. We don't see any difference between no white phase and optimized white phase. Optimized white phase is what we have looked at so far. And the main reason for not observing any difference here is that when we don't have any CAV, white phase is not going to be activated. But we see that at 10% CAV, there is a small difference between no white phase and white phase. And when we increase the CAV market penetration rate, that difference increases. And when we are at 90% or 100% CAV penetration rate, we see that the presence of this new white phase that we have introduced in this study makes a big difference and yields significant reduction in total delay that I am showing on this graph.
I'm sorry, what was in white phase? Can you repeat this?
What was white phase?
Yeah.
Yeah, white phase is the phase that we have introduced that allows CAVs to control the movement of traffic, and vehicles can access the intersection from conflicting movements without having a red or green phase. So maybe this figure here shows the white phase, how it is working. On the right, on these two, I have 80% CAVs. Left-hand side shows using a green and red phase. Because here we have 80%, you see a lot of white phase activations, and you can see that these blue cars that are CAVs, how they can control the flow of traffic through the intersection.
So do you mean that there is a communication between the vehicles? That's how they are controlling it?
Yeah. Okay. There is a communication between vehicles and also between vehicles and the transportation infrastructure there that determines these phases.
Thank you.
Sure. Also, I'm showing you total delay here as this animation goes forward. And on the left-hand side, you see the difference that for green and red, vehicles have to stop. And so you have these queues that we don't have it on the right-hand side. Okay, here I have another table that shows some more results here. So if we look at the CAV market penetration rate, pretty much in each of these columns, we see that with increasing the market penetration rate, the average delay goes down. The new scenario that I'm showing here is that if we only use white phase, and we cannot have that in 0%, but with 25% and more, we can enforce that. It's just much harder to find feasible solutions for this optimization program. And if you look at one certain CAV market penetration rate, again, we see that market penetration rate, we see that no white phase has the highest delay. When you only enforce white phase, you have some benefits in delay, but when you optimize the white phase, we see more improvements. And for higher CAV market penetration rate, optimized white phase and white phase only become very similar, but it's not always feasible to enforce the white phase only. So we see positive impacts on traffic operations. How about speed variance? And does white phase increase speed variance, or does it reduce it? So that's what I'm showing you here. On the y-axis, you see the speed variance. On the x-axis, CAV market penetration rates. And you see the blue bars are for no white phase, and the green bars are for optimized white phase. And you can see that there is a big difference in speed variance when we use white phase, because CAVs pretty much smoothly control the flow of traffic when they go through the intersection. So this is what we see with white phase in a signalized intersection. What happens if we get rid of the signal controller altogether? So that's what I will be talking about over the next few slides. We started this work with having a central controller that communicated with all of these vehicles and providing them with a trajectory to go through the intersection. And then we decided to make that a distributed approach and use the computational power that is available on each of these CAVs. So we came up with a distributed approach that each CAV optimized its own trajectory while communicating with each other to go through the intersection. I have the publications that we have on this on the right hand side, and now I'm just going to jump over the results and take a look at some numbers together. So the approach that we used in terms of formulation, solution technique, implementation is similar. Of course, the details are a lot different, but the overall big picture is the same. So we are looking at a similar intersection. I'm showing you some information about desired speed, detection range, and things like that. Our planning horizon here is 30 seconds. Study period is 15 minutes. And here I'm showing two different demand levels. One is low, the other is very high. This is 1500 vehicles per hour per lane that goes through the system. I'm showing you travel time for distributed way of implementing the signal-free control in intersection, and for central way of doing that. These are pretty much the same. Central is giving us better results as expected because we haven't made any relaxation in the optimization to make it distributed. The fully actuated control, this is pretty much the state of the art. I'm just showing it for reference. It's giving us a lot more delay. And we see pretty much similar trends for throughput. Now for low traffic demand, the number of vehicles that are processed are not that different. But if you look into high traffic demand, you see that the distributed or the signal-free approach has a lot more vehicles that are processed in the intersection compared to the actuated approach. And the reason that I don't have any number for central approach is that it couldn't deal with the complexities of the problem when the number of vehicles were too many. The distributed approach didn't have any issue there. And this figure pretty much shows the outcome of what we did when this is implemented in VSIM. The color coding that I'm using here, green means that vehicles are speeding up, white, the speed is fixed, either stopped or fixed, and red means that they are reducing their speed. On the left-hand side, you see a typical actuated signal, and on the right-hand side, you see the signal-free control that we have. And what we have here is that you see there is a big difference in how vehicles are processed when all of them are CAVs compared to none of them on the left-hand side. So the next topic that I'm gonna touch very quickly is about roundabouts, how we can improve the flow of vehicles in a roundabout when we have a combination of CAVs and human-driven vehicles. And our idea here was that we have this formulation that works in a signalized intersection. It should be pretty easy to bring it to roundabouts and control the flow of traffic there. And we started with that in mind, and boy, we were wrong. This was a lot harder than we thought because of all the merging, merge, diverge, and weaving maneuvers that happens in a roundabout because of the presence of that circular roadway that we have there. And pretty much we started with thinking that this is gonna be easy, and we ended up pretty much redoing everything that we have done for signalized intersections. And so eventually we got it right, and I'm gonna show you some details. So the reason that we think roundabouts, in roundabouts we could see significant improvement is that if you look at this figure and assume that both of these are human-driven vehicles, vehicle 2 doesn't know where vehicle 1 wants to go, and as a result of that, if does not have enough gap, it's going to wait until he or she knows what is the destination of vehicle 1. If we know that vehicle 2 can really go without having to have to wait for a gap, and this connectivity could significantly improve traffic operations in a roundabout. Automation also can do that because it can streamline this merge, weave, and diverge movements that we have in a roundabout. So we use the same drill here: formulation, solution technique, implementation, and I'm going to jump to our case study here. We applied this approach to a roundabout that we have on NC State campus at Hillsborough Street and Dixie Trail and Friendly Drive. We used 3 demand levels of 400, 600, and 900 vehicles per hour per lane. And I'm going to again talk about the capacity without providing you numbers here, but 900 vehicles per hour per lane is really a big number for a roundabout. And roundabouts are really good when traffic demand or flow is low. When they reach to 700, 800, 900 range, it's really high for a roundabout, and you're going to see long queues there. We also tested this approach for CAV penetration rates from 0 to 100 at 20% increments. So here I have a 0%, which is a simulation, VSIM simulation of vehicles, and you see that by increasing the CAV market penetration rate, total delay decreases. And something that we observed that I really don't have a good answer for that is this huge drop or reduction that we have in total delay when we have a lot of CAVs, 80% here compared to 100% CAVs. And you see also a significant increase in their average speed when they go through the roundabout. We also looked at hard acceleration in the roundabout, actually decelerations in the roundabout. So you see that when we have 0%, the frequency of them is in the order of 45 or so, and when the CAV market penetration rate goes up, the decelerations, the frequency of hard decelerations of more than 13 feet per square second decreases significantly. We have trajectories of how vehicles travel through the roundabout on this slide, similar to the previous cases that we observed. When we increase the market penetration rate, the flow of vehicle becomes smoother to go through the roundabout. I have an animation here that shows how vehicles are going to go through the roundabout, but I want to skip it and transition to freeways and lane drops because I don't want to take too much of your time on Friday night. So that would be the last topic that I will be talking about. So we have tested our approaches for controlling CAVs in signalized intersections, roundabouts, and we wanted to bring them to freeway sections. And here I'm showing you a section of a freeway that has 3 lanes, and then 1 lane drops, and then we have 2 lanes to go forward. And what you observed in these sections is that we see a lot of lane changing, which decreases the capacity, and we can see congestions even at demand levels that are far less than the capacity of these 2 remaining lanes. And our hypothesis was that if we have good lane changing for CAVs, we can increase this capacity and reduce the number of stops and risk of collision. So we again went through the problem formulation, solution technique implementation. I'm going to jump to the results. So I'm showing you here 3 different demand levels, 900, 1500, and 2400 vehicles per hour per lane. One case that I'm showing you here is when we have 4 lanes open, and then we reduce it to 3 lanes. The speed limit is 60 here, and we tested this for more cases. We had 3 speed limits of 60, 65, 70, and different configurations of open to closed lanes. Now for autonomous lane changing, you see average travel time here, which is pretty much fixed. Even when you increase the demand, you don't see a significant increase here. But if you compare it with human-driven vehicles lane changing, you see that when we increase the demand, you see an increase in the average travel time. That's not a lot when we go from 900 to 1500 because we are still under capacity. But when we get to 2400, you see a significant decrease, significant increase in the average travel time. And also you see the differences that I have here. I have a visualization on this slide. On the left-hand side, you see a heat map of speeds. You see that all of them are blue, so it means that speeds are very close to 60 miles per hour. This is for autonomous lane changing. For VSIM simulation of human-driven vehicles, you can see that we have a lot of red colors here, meaning that vehicles are stopped or they're going really slow. So here I'm looking at safety and time to collisions. For autonomous lane changing, we did not observe any near crash condition. For human-driven vehicles, we see a good number of collisions, especially when the demand increases. And here again, I have one simulation that shows the difference between these two. If you look at this part of this figure, you see that the vehicles are slowing down, and we have a congestion that starts here and spills back because these vehicles, when they want to do a lane changing, they cannot do it very efficiently, and that's not the case on the left-hand side. So that brings me to the conclusion. So on the white face side, we observed that using CAVs as mobile traffic controllers in cooperation with signals significantly improves traffic conditions. They can form platoons of HVs and navigate them through the intersection. And eventually, white face significantly improved traffic operations. With the 100% CAVs, we could get rid of traffic lights and see significant reductions in delay, and also pretty much the same trends were observed in traffic in terms of improvements in traffic operations in roundabouts and freeway segments. Now, the work that we did has a lot of assumptions, and hopefully in our future work we can relax some of those and include other users such as pedestrians, bikes, and buses. We have started to look into including pedestrians and buses in our work now. We assume perfect communication between vehicles and the controllers. That's something that needs to be revisited and at least simulate communication failure or delays and see how they're going to change the operation that we observe. We would like to be able to account for different human driver behaviors, vehicle propulsion capabilities, and CAV response, and also analyze other highway facilities and geometries that we have, and also transition to hardware in the loop tests, and hopefully in the future in real world tests. I want to very quickly also introduce my graduate students that did a lot of work in this area. These are only those graduate students that were involved in CAV activities that we have. Mehdad and SMA are already graduated. The other two are still with us. And with that, I want to thank you all, and I'm available for any questions. Thank you.
Thank you.
Great, thank you so much.
I have a quick question. I imagine that you could probably optimize the control, the distributed control, to have greater throughput in the intersection than a human rider would be comfortable with. I mean, you're going to be very, very close to those other vehicles. And is that part of any of your research?
Yeah, we can assume smaller or shorter gaps between vehicles that are at a point that a human driver is not comfortable with. We try to not go to the extremes, and if we go, we can see even more improvement. But as of now, the way that we have designed these is that we try to to maintain the same gap. Our reaction time is a little bit shorter than a normal human driver.
Thank you. And other question, have you considered, there almost needs to be a fail-safe mode such that when you violently have to leave white phase because the communication system went down abruptly, that may also influence the minimum distances that you can have between vehicles.
Yeah, precisely. And that's one of the things that we have started to look into it and see first from a numerical perspective, if we have, let's say, a failure in communication, what is going to happen to our results? And hopefully in the future, from a methodological perspective, what can we do in such conditions so that we don't have a terrible situation and go forward in that regard.
Thank you.
Thanks a lot. Yeah.
I have also a question. Thank you very much. And my question is there any chance of arriving at something like a live lock in your system?
Say it one more time. Your voice is breaking up. I didn't catch the question.
Okay. Is there any chance of experiencing live lock in the system?
Any chance of experience what?
Kind of deadlock.
Hidden lock?
Let me write it on the
Deadlock.
Lock or
Deadlock.
lock.
Yeah, I'm gonna look at the chat. Let me stop sharing my screen so that I can see everything.
Deadlock or lock, in the sense that, for example, all of the vehicles are waiting for each other to make a decision, or they are stuck in there in that sense.
Oh yeah. We had that situation that all vehicles were trying to, they were slowing down, and they couldn't go through. And when such a situation is about to happen, we have like strategies to go around it, and either come up with a priority to start moving some of them based on the time that they have arrived, or strategies like that. But yeah, that could happen. And when we were formulating the problem, we were seeing that, and we tried to come up with ways to pretty much avoid it.
Okay, thank you. And
Sure.
my other question is, how scalable is the system? Is it possible to quantify?
Yeah, that's a very good question. So when we solve the problem following a centralized architecture, it's not scalable. The runtime, for example, for 15 minutes of simulation is several hours. But when we go to when we use a distributed approach, especially, for example, the animation that I showed you for the signal-free control, that is real time. And the assumption there is that each of these vehicles have a good computer on board, which may not, or maybe or may not be the right assumption. But with that assumption, it could be real time, assuming perfect communication, assuming that each of them are going to find answer to the optimal solution within the same amount of time. But if you bring those uncertainties, it may not be real time. But in our perfect world, with all of those assumptions, it could be real time if it is distributed.
Thank you very much.
Sure.
I have a quick question. So my question is, how do you switch between the standard signal phases and then the white phase?
Yeah, it happens in the optimization. So you have a signal head for white, and if there is a need to have that, the white phase is going to be shown, very similar to the transition that you have between green and red. So if you want to go from white to green, pretty much you just go directly from white to green, because the right of way is increased. But if you are going from, let's say, green to white, you have to show a yellow signal. If you go from white to red, you need to show a yellow signal, and so forth.
So does that mean like you are not following any order for switching between the phases?
Say one more time.
Do you follow any order for like switching between the phases? Like in the real world, you switch from, let's say, from red, then you go to yellow, then green. So like now you've included an additional phase, which is the white phase. So like, do you follow any pattern or any order, or you always have to switch? Like you always give priority to the white phase?
No, we don't always give priority to the white phase. It pretty much is up to the optimization model to say which phase is going to be the best to be used. Now, we can add constraints that introduce different orders for these to be used. But as of now, pretty much the logic that I told you is that if you go from white to green, it's just a direct transition. From green to white, you're going to have to use a yellow. From white to red, you're going to have to use a yellow.
Okay, thank you.
Sure.
May I ask a couple of questions?
Sure.
Okay, on slide 22, when you were comparing signalized versus non-signalized,
Mm-hmm.
the one with non-signalized, you mentioned that congestion, vehicles are able to basically in the intersection to go through, but what about the level of comfort?
Level of comfort in the signal free?
Yeah, in the signal free, because do you even sit in those cars?
Yeah.
It's like riding in Tehran.
Yeah. So I have simulations of those that I have shown before from the inside of the car. It feels scary, but with those simulations, you don't see how much they speed up or slow down. And we have one term, a couple of terms that we have added to the objective function of the problem to precisely account for that. One is that we want to minimize the difference between speed for one vehicle over two consecutive time steps, so that you don't jump, for example, from 40 miles per hour to, let's say, 10 miles per hour in half a second or so, right? So we want that to be smooth. And also, we minimize the absolute value of the acceleration rate. So we don't want the driver we don't promote speeding up or slowing down abruptly. And those, when we look at the speed profile and also acceleration profile, looks like that it makes them a little bit smoother, but still it's not as smooth as a conservative human driver, because some human drivers may be going more aggressive than that. But there are ways to improve it with changing the weights that we have defined there. But yeah, that's something that we have it there.
Also follow up, you mentioned about platoon, then I assume that you have looked in the string stability as well of the platoon.
Well, stability in what sense? If the platoon remains the same, or if you mean if vehicles are going to be added or removed from the platoon?
From the platoon, that's right, between the first and the last one, imagine.
Yeah.
How are you going to do that? Yeah.
Yeah, as of now, we assume that the platoon does not change over the planning horizon. Okay, so if we have 30 seconds that we predict over that, we assume that the platoon is the same. Now, when we observe the network every 0.5 or 1 second, we have a logic that based on that, we define a platoon. And that could be different than the platoon that we defined 1 second ago. But in our optimization, we just assume that they are the same. And there needs to be more work to be done, I think, on the stability of the platoon and how that is going to change our approach. But we have that limitation there that we just assume it to be fixed.
Okay, thank you.
Sure.
Okay. Any other question? So I do have a couple of other questions, but I think it's already 4 or 5. I don't want to keep people waiting here Friday afternoon, but I'm sure that I'm going to have opportunity for discussion later with Dr. Hajbabaie later. And
sure.
I'm sure that this has been excited so many thought and questions, which hopefully we do have the chance to discuss later.
Yeah, and I will be happy to do so later. And also want to thank everyone for listening to this presentation. I wasn't expecting it to take this much time, but looks like that I went overboard when I was talking. I didn't realize that.
Yep, enjoyed it. Thank you so much.
Thanks a lot. Have a great weekend.
Okay, thank you so much. Thank you
you.
so much. All right, great presentation.
Thanks a lot.
All right,
Have a good one. Bye now.
bye-bye.